Welcome. In this video, we'll be looking at ionic compounds. Let's get into it. Alright, so here's a quick definition. Ionic compounds are compounds that are held together by ionic bonds formed by the transfer of electrons between atoms. Okay, so the first thing you should be able to do in regards to ionic compounds is identify them, because often you'll be given a mixture of different compounds and you need to identify whether a substance is ionic or not. So an ionic compound typically occurs between metals and nonmetals. And let's identify that on the periodic table over here. So let me just draw this staircase. And these brown elements over here, these are the metalloids. So I'm just going to draw a staircase here. That's a really helpful way of thinking about it. And everything to the right of this staircase you can call nonmetals, right? That's like a general category you can put them under. And everything to the right of this, to the left, are called metals, excluding hydrogen. So hydrogen is actually a nonmetal. But everything else is metals, and everything to the right is nonmetals. And for future reference, we'll be looking at nomenclature with these. This area here, everything here, are transition metals, and they're a type of metal, right? So ionic compounds typically are between metals, something from the left side here, and nonmetals, something from the right side over here. And they can also occur between metals and polyatomic ions. And polyatomic ions are just groups of charged ions that groups of is a compound that carries a net overall charge. And we'll look into that in a future video. But for now, it's important to realize that a nonmetal and a metal, or a metal and a polyatomic ion, typically constitutes an ionic compound. So that's a quick way of identifying whether a substance is ionic. All right. So what causes ionic compounds? What's the point? There are two main driving forces behind ionic compounds, and they are electronegativity and the idea of stability. Now, I'm sure you've seen these numbers before, the 2, the 8, and the 2, and this is like a way of remembering how many electrons each shell can occupy in the Bohr-Rutherford diagram, right? The first shell can have 2, second shell can have 8, third shell can have 8, and the fourth shell can have 2. And the Octet Rule states that an atom is the most stable, it's in its most stable position when its outermost shell is fully occupied. When the outermost shell either has 2 electrons, 8 electrons, 8 electrons, or 2 electrons. That is when an atom is at its most stable position, right? So if we look at these examples down here, we can kind of see what that means. So here, the outermost shell of this particular compound has 8 electrons, right? 2, 4, 6, 8. That means that it is in the most stable position possible. This one only has 2 electrons. But remember, the first shell can have 2 electrons, right? That's the maximum it can have. So since it's at its maximum occupancy, yeah, it's at its most stable position. But here, it has 1, 2, 3, 4, 5 in its outermost shell. The second shell can hold a maximum of 8. So since it's not at its maximum, this is not in the most stable position possible. And you could think of it as the atom's drive to get more electrons or less electrons and to be in the most stable position possible refers to its electronegativity, its tendency to attract electrons. And you'll see what I mean. But you can think of it as all atoms trying to get into this stable position. And here is an example of how it works. So here we have an ionic compound. This is a popular ionic compound, and it's sodium chloride. NaCl, sodium chloride. And here are the Bohr-Rutherford diagrams for a sodium atom and a chlorine atom. And what happens here is kind of like a conversation. Sodium hits up chlorine and tells them that, I have an extra electron here. So let's make a deal. If I give you this electron, I'm happy because my outer shell now has 8 electrons. I'm stable. And if I give you this electron, then your outer shell will also have 8 electrons. You can think of it as like a business transaction, but something that's mutually beneficial, because in this instance, both of these atoms will turn into ions, in which they will both have complete valence shells, and the Octet Rule will be satisfied. Right? That's kind of the driving force here. That's why these ionic compounds occur. So what happens is that this transaction goes down. Sodium gives its electron to chlorine. It's not like covalent compounds. There's no sharing. Chlorine just takes it. It's gone. So what happens here is that now the sodium atom turns into a sodium ion. Why is it an ion? Well, because sodium has 11 protons, and since it lost an electron, it only has 10 electrons now. It now has one more proton than electron, so it carries a net positive charge. Ions with a net positive charge are called cations. That's an important term to note. You'll see it a lot. Ions with a positive charge are cations, right? And the same thing happens in chlorine. It turns into an ion because originally it had 17 protons and 17 electrons. It gained the electron from sodium, now has 18 electrons, 17 protons, one more electron than proton, overall net negative charge. And an anion is going to have a net negative charge. So that is the name for a negative ion. All right, and this is how you write it out with the chemical symbols. And what happens here is that since it's a positive ion now and the negative ion now, they're going to attract each other and they're going to form an ionic structure, an ionic compound, right? And what this is going to look like here, and this is like a brief snapshot of it, is going to be a lot of these ions packed together in what is called a crystal lattice. And a crystal lattice is basically a 3D cube structure, something like a cube, where there's a bunch of ions packed together, positive and negative, packed together in a very dense space. And this is a 2D representation of it, but you can think of it as if it was supposed to be a cube, right? And you would see a bunch of these positive and negative ions tightly packed together. And this crystal lattice structure is something that's unique to ionic substances. And this structure is also responsible for a lot of the ionic substances' properties. So just to clarify here, these ions, the ions from the cations and the anions, they are packed together tightly in some kind of cube structure, and that's referred to as a crystal lattice structure. And most ionic compounds follow this structure. All right, so now let's look at some properties of ionic compounds. And some properties that are synonymous with ionic compounds is the fact that they have high boiling and high melting points. As we mentioned earlier, this is due to the crystal lattice structure of the ionic compound, right? These ions are packed together very, very tightly. And they also have a strong net charge. It's going to be a full charge. It's full positive, full negative. It's not a dipole. It's not a partial charge. The magnitude of the charge is very high. So it's going to be a high magnitude of the charge. And the distance is very low, right? Because they're so tightly packed together, they're kind of like sardines in a can. They're very, very stuck together, right? So that gives it a very high Coulombic attraction. It's a high electrostatic attraction between the ions that make it very, very tough to break apart. This goes back to Coulombs' law. These are the variables that are dependent on Coulombs' law. And since the electrostatic forces, the Coulombic attraction in the ionic structure is so strong, it takes a very high temperature to be able to kind of break that apart. That's why they have high boiling and high melting points. The electrostatic forces within it it's held together very, very well, right? So it's going to take a lot of temperature, a high degree of temperature to break that down. Another property is that ionic compounds are electrically conductive, that they're water soluble. Now these two kind of go hand in hand, so we'll deal with them together. And here's a little diagram, not an A+ diagram, but it's a diagram nonetheless. And here you have an ionic compound. I kind of drew the bonds here between the ionic compound. And what happens is that when you put an ionic substance in water, the ions in the substance, they kind of disassociate. They break apart, right? Disassociate's the chemical term for it, but really does break apart into its individual components. It's no longer in that crystal lattice structure. As you can see over here, it's just floating apart. It's kind of becoming its own person. Why does this happen? Well, what happens is that the ions are attracted to the partial charges in water. The water molecule is very polar. And then it sort of breaks apart and it's more attracted to the water than it is to the other ions. You can think of it as the ions kind of found a new friend in the water molecule and they don't want to hang out with the other anion or the other cation that was previously in the structure, right? So it finds a new friend and it goes off and breaks apart, right? So when these ions associate, the overall substance, the solution, becomes electrically conductive. Why? Because ions are charged material. As you looked up here, they are, whoa, I don't know where I ended up there. They have a net positive charge or a net negative charge, right? So that means these positive or negative charges are capable of conducting electricity, right? So that's why ionic substances are electrically conductive. Because they're water soluble, they're also electrically conductive. It's important to note that ionic substances are not electrically conductive in its solid phase. It's only conductive in its liquid phase once the individual ions break apart. That is an important note. All right. The final property, and something that I've always had a bit, confusion about, is the idea that ionic substances are brittle yet hard. Now you may be wondering, what does that even mean? How can something be brittle and hard? Aren't they like opposite terms? So let me just show you what that means here. So this is like a picture of a normal ionic substance, the way the crystallized structure is arranged. It's basically the cations and the anions alternating, right? This makes a substance hard. As you mentioned earlier, high electrostatic forces, it's very packed, it's very dense. Ionic substances are going to be hard for that reason. But the reason why it's brittle is that if you apply a slightest force to it, right? Say I were to, get a ball and pow, attack this, right? Say everything moves over one, right? The top layer moves over one. Suddenly, the same electrostatic forces that held the compound together are trying to push it apart. Okay, so here, these are opposite charges, right? This is negative, this is positive. These attract. But what happens when you push this apart is that now it becomes disaligned. The negative is with the negative and the positive is with the positive. Like charges repel. So what happens is that the compound, forces itself apart, right? The same electrostatic forces work against itself, and now it's going to break easily. That's why it's brittle, because the slightest amount of force could disalign this delicate structure, and then the ion would would break, and would kind of push away from itself, right? So before, this alternating fashion helped the ions stay together, right? Helped the structure stay together because like charges attract, but now opposite charges attract, and then here like charges repel, so the ion kind of breaks apart, it becomes brittle. All right, so hopefully that made sense. So in this video, we looked at what an ionic substance is. We looked at the definition, identifying ionic substances. We looked at electronegativity and the Octet Rule. We looked at ions and how they're formed. And we finished off with some properties of ionic compounds. So hopefully you enjoyed the video. If you did, click the like button, subscribe to the channel, and I can't wait to see you guys next time.